Our result in A told us that the membrane potential is a non-equilibrium system. There must be a particular machine that is organizing and also controlling membrane potential. That is the sodium potential pump. Now in A we learned that the ion concentrations will lead to membrane potential which is not what we can measure. Further, there's a very abnormal behavior of sodium. For sodium, we would expect that the Nernst potential is positive, yet we know the cell membrane has a negative potential. So these are the two effects that we would like to reconcile. Now, given this argument, we have to consider that ions are out of equilibrium, which means there must be an ionic current through the membrane. Now it's now handy to transfer this view into an electrical equivalence. For that we define an electric equivalent circuit where we have the membrane connected by some battery, which defines the Nernst potential, and a resistor. Hence, if there is a potential and if the resistance is not infinity, it's clear that there must be a current. Now the ion flux we now can just represent as Ohm's law. So the ion flux, which is the current, Ji, where I is any of these ions, potassium, sodium, chloride, is equal to delta V, which is the membrane potential, minus Vi, where Vi is the respective Nernst potential of the respective ion, times the conductivity, which is the inverse of the resistivity. Now it's good to briefly check the units. So the flux J, the units of the flux J, is the number of charges per second and square meter that is traversing the membrane. Hence the specific conductivity, Gi, has the units of 1 divided by ohm and square meter. Now the ionic flux, which is an electrical flux, must be paralleled by a flux of ions, of particles. Well, for the flux of particles, phi, we know how to couple that to the permeability coefficient, Pd, and the flux is equal to the permeability coefficient Pd times the gradient in the concentration. Now this particle flux has to be equal to the respective ionic flux given by Ji divided by Zi times the electric charge. And if we assume for the time being that delta V actually is 0, we obtain a relation between the permeability coefficient and the resistivity given by Pd times delta C is equal to kBt divided by Z E squared G of I log of the concentration inside divided by the concentration outside. Now further simplifying and taking into account that the concentration difference, relative concentration difference is small, we obtain the final equation which relates delta C and the permeability coefficient Pd with kBt divided by Zi e to e squared times Gi delta C divided by C outside. Now solving for the specific conductivity Gi, we find that Gi is equal to Zi times E squared divided by kBt Pi times Ci. Now applying our finding to the situation in the cell, we see that the specific conductivity is proportional to the specific permeability of the ions. Hence, for a cell holds that the conductivity of the chlorine is much larger than the conductivity of the sodium, which is larger than the conductivity of the potassium. This particular finding leads us now to the final conclusion. Since the conductivity of the chlorine and the sodium ion are much larger than the conductivity of the potassium ions, any potential made up by chlorine or sodium will be washed out in a very fast way. And it's only that the low conductivity of the potassium ions will lead to the potential of a membrane. You also could visualize this that we basically have a network of parallel resistors, and there we know that the final conductivity is determined by the smallest conductivity. Hence, our conclusion is the membrane potential is set by the Nernst potential of the potassium ion. Now, if you look back into the numbers, you will find that indeed the Nernst potential of the potassium ion is in the order of minus 60 millivolt, which is what we measure. Yet what we now have to consider is the strange behavior of the sodium, the so-called sodium anomaly. Well, the sodium Nernst potential actually is positive. What this suggests is there must be an additional outward flux of sodium ions from the cell. Hence, by extending the equation for the ionic flux that we had before, now just for sodium, we have to state that the sodium ion flux is equal to the conductivity of sodium ion divided by E times delta V minus the Nernst potential of the sodium ion plus an additional flux of sodium ions, which is caused by an active pump. Now, this is what you actually also can measure. So here you see an experiment in which the outward current of sodium has been measured as a function of time. Now, after 120 minutes, so the flux is somewhat decreasing, but after 120 minutes, the cells are incubated with a toxin which will block a certain protein in the membrane. And you see that the flux vanishes. If you wash out this blocker after 200 minutes, you see that the flux comes back again. So indeed, there seems to be a specific protein which pumps sodium out of the cell. Now, surprisingly, you can do the same experiment also for potassium. Take the same toxin, and you will again find that now the potassium is also pumped, yet it's pumped into the cell. Now, those were the indications that there must be an active process of one particular protein which pumps sodium outside to the outside and potassium inside. Now, even more detailed studies showed that the pump runs on ATP, and by transfer of using one ATP, it pumps 3 sodium ions to the outside and 2 potassium ions inside. Now, in the meantime, this protein has been identified and crystallized, and you can get high resolution structures of this particular protein. Okay, so let's wrap up lecture 6. So what are the take-home messages? Well, first we looked back into physics of life 1 and reconsidered the Nernst potential, which relates the ionic difference in the ionic concentrations of in two compartments that leads to an electric potential. We further considered the membrane permeability, and we found that the membrane is highly permeable for water, but almost impermeable or moderately permeable for ions. We found that the membrane potential is given by minus 60 millivolt, determined by the concentration difference in the potassium ions. In order to keep this minus 60 millivolt stable, there is a special machine in the cell membrane, the sodium-potassium pumps, that also creates the sodium anomaly that has been found. And it's working on, it's an ATPase, so it hydrolyzes ATP, burns ATP. And by pumping 3 sodium atoms outside and 2 potassium ions inside.